Okay, thank you for coming. Thanks, organizer. I will stay here because my remote mouse is not working. So, and I will have to use the mouse. I will talk about sonification or audification in real time of ordinary differential equations. That means take the solution of these equations and convert that to sound from two perspectives, as a pedagogical tool to explore the parameter space, the onset of bifurcations, and transition to chaos, and also as a sound synthesis method, especially for some musical instrument models that we are working with. And this talk is also in joint with Antonio Ortega Bruc and Darío Ruiz from our group. It is the LabSol, the Acoustic and Sound Perception Lab at the University of Quilmes, Buenos Aires, Argentina. And this is also with the support of CONICET, that is the National Research Council. And this is the plan of the talk. Let's say like this. Okay. So we have two parts. In the first part, in red, I will present the background of our project, who we are, what is our motivation, and then I will move into the explaining what are the advantages of translating the numerical solution of nonlinear dynamical system into sound, both from the pedagogical and from the mathematical modeling point of view, and also as a tool for sound synthesis. And then I will finish the first part presenting a small package that we recently developed. Actually, I think that it should be registered today, but we can try. I will give you the links at the end. And in the last second part, in blue, depending on how much time is left, I will show you one or more examples with sound. And also, I will show you how to run this package from the REPL. Okay, then I will start commenting on my co-authors, Darío and Antonio. They are musicians and PhD candidates in our group. And with them, we are looking for modeling wind musical instruments from the paradigm of nonlinear dynamics. That means we try to extract the essential ingredients of the dynamics with minimal models, hopefully preserving some of the expressive capabilities of the original instruments. And we are interested, for example, in the link between some bifurcation in our mathematical model and some sonorities in the real instrument. For example, multiphonics in the saxophone, to get some insight on the process underlying this phenomena, but also because we want to make a digital replica of the instrument. And I would say we were talking a lot during the morning and about digital twins. I will not say digital twins because we are not interested in an exact copy of the sound. We are interested that the dynamical change of regimes are the same in the model and in the instrument. And to put this into test, we are working with musicians interacting with the model in real time. Okay, and this is why we are interested for the moment with a computer model with a MIDI interface, but we are working with sensors in a mute instrument and eventually an embedded system. This is why we're interested in minimal models. And this project is also related to a more musical-oriented project with Martin Prosia. We were working also with multiphonics in the saxophone, but more from a cognitive perspective, But now we are doing the psychophysical experiments with the package in Julia that I will present today. And finally, there's also a link with another project in our group that made a digital replica for the bandoneon, or bandoneon. I don't know if you know this is the emblematic instrument of tango, also of the city of my city. And there's a big problem because the bandoneons are really very difficult to manufacture and to obtain. Actually, most of the bandoneons that are around are almost 100 years old. So to have a digital replica is something that is really important. But for now, we are using for this project bandoneon 2.0 more classical sound synthesis methods, but we are working in a dynamical model of the free reed also. And finally, to finish the presentation of our group, I will say that this is framed in a more broad project or program that we can loosely call generalized lutherie, that goes beyond the digital lutherie, that the idea of a replica of a real instrument or to create new digital instrument is. We are interested in many other ways that we can create sound and also modify sound while it's propagating through the air in a situation of musical performance. This has led us to work with, for example, acoustic metamaterials as an extension of musical instrument that can work at the scale of a room. For example, the sonic crystal room can modify the sound that is emitted from an orchestra or from singers. And we are not only doing scientific research, but also we made an opera that will be re-released in next September. Okay, so coming back to our motivation, and in my particular case, my background I'm a physicist, and my background is in applied nonlinear dynamical system and acoustics. So the idea to join these two worlds has a long history. And at the beginning of the 2000s, I was working with my former advisor, Gabriel Mindlin, and a colleague, Marcos Trevisan. We were working in dynamical models of the vocal folds for speaker recognition. And then Gabriel developed further the model and for birdsong, and now his group is one of the leading reference in this field, and is still for me a source of inspiration. And more recently, I get involved in a more pedagogical part of the nonlinear dynamical system, in a more broader project of acoustic education that was led by Gabriel Catren of the University of Paris. And in that photo, it's a workshop, not only in the academia, is in the wild. We gave a workshop in the context of an art residence that was called Deeply Organized Chaos, and it was done entirely in Julia and Pluto. And we end that workshop with a jam session making sound from ODEs. Unfortunately, but at that moment, we used Super Collider because this package was not yet developed. But I take this experience because for people that have no mathematical training, the possibility to play with the model and to make sound is a really nice way to approach to this kind of problem. So this idea, this experience, together with the need of the model exploration for the mathematical model of the musical instrument, lead us to try to develop the package that we'll present today. That the idea is not only to have this intuitive access, but also that, for example, for some model of the musical instrument, I will show you at the end a model of a saxophone. For example, the parameters are the blowing pressure and the pressure of the lips on the mouthpiece. So we can control these parameters, and the musicians can have a more intuitive interaction with these parameters. And of course, also this can be used also for sound synthesis and live coding. Okay, there are many advantages of using ODEs as a sound synthesis. I will only say here that you have the more traditional model, methods that are like FM or granular synthesis that work extremely well. They're extremely effective, but not always have some relation with the acoustical phenomena. And on the other side, you have models that are physically based, but are much more expensive in terms of computation. The idea is that the models based on ODEs can stay in between, having advantages both. And then we start to develop this idea of making sound with ODEs with the two most powerful platforms for sound synthesis that are Super Collider and MaxMSP. In the case of Super Collider, we use a library that was developed by Daniel Meyer as the one sample feedback that implement a fixed step, because you know in audio you have the sampling rate, so you need the solution at fixed steps. And also in MaxMSP, we implemented an object that was written in C that it takes the Rungekuta and with fixed step. And here we are taking the numerical algorithm to the domain of the software used for sound synthesis. The idea is going to other way around, giving the power to Julia to real sound capabilities. Of course, using this wonderful library, I think that it's not necessary to explain that the algorithms that have differential equations are extremely efficient. And we also join this with PortAudio, that the idea is to use PortAudio to call the solvers of differential equation in a dedicated audio thread that is managed by PortAudio. Okay. So are the main features of the package. The idea is to use DifferentialEquation.jl and leave. At the beginning we start to use there is a library that's called PortAudio.jl, but the problem is that it's not easy to access to the asynchronous callbacks that are necessary for audio, because you need to refill the audio buffer as soon as you need. Okay. So we use the wrapper of the PortAudio that exists already in Julia. There's PortAudio JLL, and the idea is that the main structure is the DE source, that it acts like like a ODE problem in the sense that it receives a function that defines the problem, or two functions in the case of stochastic differential equation. The second function is the noise, and also receive an array of initial conditions, an array of parameters, and stores this D problem, also a callback for PortAudio, and the state between callbacks. Okay, and then the idea is that when we make sound from this the source using start the source, and that creates a PortAudio stream, and the callback asynchronously invoke solve to refill the audio buffer. We also try at the beginning. We thought that maybe using the integrator interface was more efficient, but we made some tests, and the solve is higher level, but it works well for our purpose. And the good thing is that we can change the parameters on the fly. Okay, not only the parameters of the problem, but also there's channel mapping that we say which variables of the model are mapping to which audio outputs. Okay, and also there is a time scaling, of course, because the time in the differential equation is not related to the real time. So we can make a short demonstration here. So we are using real-time audio diff-ec, and we define a function. In this case, it's a very simple differential system of two differential equations that it's based on the Rayleigh model of a reed of a clarinet. So it's just a nonlinear dissipation there, and some negative dissipation, and a nonlinear dissipation of cubic. And then we can define our source, invoking the source, the function, and a set of initial conditions and two parameters. The two parameters of the model are: the first one is the parameter that when cross the zero, you get a Hopf bifurcation. So now we start with the system off. And the second parameter is the elastic constant. So it will control the square root of this, it will relate it to the frequency. Okay, so now it's defined, and then we can start our source and with the default output device, but we cannot listen because this time scaling now it's we need to rescale the time. So we set the scaling to 1000. That means that a time of 1 in the model is 1 millisecond. So it's in the audio rate. Okay. Now we will set the first parameter, that is the bifurcation, to the positive value, and hopefully we will hear something. No. Let's see what happened. We try this, and okay, that's strange. We try with this. Sorry. It's working, right, with this? Okay, for some reason. Yeah, but for some reason. Okay, very loud. Okay, we will switch to the. Maybe I need to do again in the REPL, but here in the Pluto notebook we have the same. But we check here, maybe it's something with the default output device. Here we have a two-system couple. This is a Duffing oscillator, and it's coupled to a Van der Pol oscillator. So now the coupling is 0, so there's no oscillation. We will move the time scaling. Oops. And then get some excitation from the Van der Pol. This is the coupling, and then I will start to move the time scaling to some. I will lower the sound because it's. And then we can control, for example, this is the time scale of the van der Pol. Okay, now we can move to lower frequencies. And increase the coupling. And eventually we can find periodic orbits. These parameters controls, but here we can change the mapping. These are the variables of the Duffin oscillator, but we can see the van der Pol. Okay. Now we are in a very far from the Hopf bifurcation. Here, some more soft sound, and also lower. And here I get higher harmonics. Then the effect on the Duffin oscillator is much more. Okay. Then if I decrease this, is more close to the typical forced Duffin oscillator with a periodic orbit. Okay. Then it's more easy to find periodic orbits in the system. Okay, so I will finish showing you very briefly the model of the saxophone. This model has 18 equations because it's with the modes of the tube, and also some variables for the movement of the reed and a coupling, linear coupling between the movement of the reed and the pressure in the saxophone. So we will start here. Now this parameter controls the blowing pressure. I can increase this. Probably we need to. Yeah, probably we need to. That was the problem before. Okay. We have to redefine the source. Okay. We were trying to get some multiphonics now. This is a Neymar-Sacker bifurcation in the model. I have a periodic orbit that has a Hopf inside, so I have a torus. It's a quasi-periodic behavior, and this is something that jazz musicians do, like, you know, and then you have this octave leap. Of course, there's some multi-stability in the model, and when you switch from one mode to the other, you have this behavior, and here you can explore the different modes. This is the first mode, and this in the right channel, the second, the third one. There's a nonlinear interaction between the first mode and the third mode. This is why it happens this tremolo. Okay? And then I will switch off. Okay, thank you.
Thank you very much. Somebody have any questions? The question is, does the real-time synthesis also lend itself to including a more complex model of, say, the human oral cavity, which
Yes, of course. And in fact, I show you one kind of multiphonic. For other type of multiphonic, you need to add the coupling with the vocal tract.
right? Absolutely.
Yeah, yeah, we are on that.
Like I play, so I know what it
Yeah,
could
yeah,
sound
it's
like,
really
right?
important.
But
Really
I
important.
think this real-time synthesis is really impressive, and the sound is actually quite accurate.
Okay.
Any questions? Thank you.
Okay.